Welcome to video lecture 3b. In the last lecture, we defined a linear code to be a k-dimensional subspace of the n-dimensional vector space over a finite field. We used the subspace structure of a linear code to easily write down the number of code words and the rate of the code. We saw that the distance of a linear code is the same as its weight. We defined a generator matrix for a linear code, which gave us an easy encoding rule for source messages. We also saw that every linear code is equivalent to a linear code that has a generator matrix in standard form. In today's lecture, we'll see that every linear code has a so-called dual linear code. The dual code will tell us a lot about the code itself. We'll define a parity-check matrix for the code to be a generator matrix for the dual code. Let x and y be two vectors of length n over a field F. Then the inner product of x and y, denoted x dot y, is a sum of the products of the corresponding components of the two vectors. Note that the inner product is a scalar and not a vector. For example, the inner product of these two vectors of length 4 over z5 is 15, which is 0 mod 5. In linear algebra classes, you might have also called the inner product the dot product. We'll say the two vectors x and y are orthogonal if their inner product is 0. Here are some elementary properties of the inner product. For all vectors x, y, and z, and all scalars lambda, the inner product is commutative, it's distributive over vector addition, scalar multiplication is associative with the inner product. But one important property of the inner product, which holds for vector spaces over the real numbers, as you saw in linear algebra, but is not the case in general, is that the inner product of a vector with itself being 0 does not imply that the vector is a 0 vector. For example, consider this vector of length 6 over z2. Then the inner product of the vector with itself is 4, which is 0 mod 2. But x is not the 0 vector. More generally, a vector of length n over z2 has inner product 0 with itself, if and only if the weight of x is even. So keep in mind in this course that since our vector spaces will be over finite fields, it's no longer the case that x dot x equals 0 implies that x is 0. I can now state the main definition of the lecture, namely the dual code of a linear code. We'll see that the dual code of a linear code is also a linear code, and it can be used to study many of the properties of the code itself. So let C be an nk linear code over a field F. The dual code of C, also called the orthogonal code of C, is denoted C perp, and is defined to be the set of all vectors x, such that the inner product of x and y is 0 for all code words y. In other words, C perp is a set of all vectors that are orthogonal to every single code word. We have a theorem that says that if C is an nk linear code over F, then the dual code of C is a linear code of length n and dimension n minus k over F. So note that the dimension of a linear code plus the dimension of its dual code is equal to n, the length of both codes. Let's prove the theorem. Let G be a generator matrix for C, and let the rows of G be v1, v2 up to vk. So these k vectors are a basis for C. Let me make the following claim. For any vector x, x belongs to the dual code of C if and only if x is orthogonal to each of the k basis vectors. The forward direction of this claim is clear, because if X is in the dual code, then X is orthogonal to every vector in C. In particular, it's orthogonal to the basis vectors for C. Conversely, suppose that V is a code word. Then we can write V as a linear combination of the basis vectors where the scalars lambda I are in the field F. And then V times X can be written like this. And using properties of the inner product, we can write the expression like this. Since each of these inner products is 0, V times X is also equal to 0. And that proves the claim. So back to the proof of the theorem. We can now write C perp as a set of all vectors X, such that G times X transpose equals 0. And that's because this matrix multiplication G times X transpose is precisely multiplying V1 times X, V2 times X, and Vk times X. And so we observe that the set of all vectors satisfying this matrix equation is precisely the null space of G. Now, since G has rank k, its null space is a vector subspace of dimension n minus k. Hence, C perp is a subspace of Vn of F of dimension n minus k, and that proves our theorem. The next important concept we'll see for linear codes is that of a parity-check matrix. Recall from the proof of the previous theorem that if G is a generator matrix for a linear code, then C perp can be described as being the null space of G. So we have this nice theorem which says that if C is a linear code, then the dual of the dual code of C equals C itself. Let's prove this theorem. Let C be an NK linear code over a field F. We proved that C perp is a linear code of length n and dimension n minus k over the same field F. Furthermore, the dual of the dual code of C is a linear code of length n and dimension n minus k, which is k. So now the dual of the dual code of C consists of all vectors orthogonal to every vector in C perp. But remember that every vector in C perp is orthogonal to every vector in C. And so C is contained in the dual of the dual code of C. But now both C and the dual of C have the same dimension k, which means that C and C perp both have size q to the k. Hence, since C is contained in C perp and they have the same size, they must be equal to each other, which gives us our result. We're ready now to define the parity-check matrix. If C is a linear code, then a generator matrix H for C perp is called a parity-check matrix, or PCM, for C. Notice that H has dimensions n minus k by n, because C perp is a code of length n and dimension n minus k. Also, C has many PCMs, because C perp has many generator matrices. Here's a nice way to construct a generator matrix for C perp, which, if you recall, is also a PCM for C. Let C be an NK linear code over a field F, with generator matrix G in standard form. So here I'm assuming that C is a systematic code. Then this matrix H, which is minus A transpose with the n minus k by n minus k identity matrix appended to its right, is a generator matrix for C perp. Notice that the matrix A has dimensions k by n minus k. And so this matrix H is an n minus k by n matrix so it has the right dimensions. Now, H has rank n minus k, and that can be seen because the last n minus k columns of H are the columns of the identity matrix. Hence, H is a generator matrix for a linear code of length n and dimension n minus k. I'll call this code C bar. Now we'll note that G times H transpose is this matrix times this matrix. And when you compute this product, the identity matrix IK is multiplied with minus A, while this A is multiplied with this identity matrix. So the product of the two matrices is minus A plus A, which is a zero matrix. This means that the rows of G are orthogonal to the columns of H transpose. Now the columns of H transpose are also the rows of H, and so every row of G is orthogonal to every row of H. And this means that the code C bar, which is spanned by the rows of H, is orthogonal to every code word in C. Hence, C bar is contained in C perp, because C perp consists of all vectors that are orthogonal to every code word in C. But now, C bar and C perp both have dimension n minus k. And so, since C bar is contained in C perp, and they have the same dimension, they must be equal to each other. And so H is a GM for C perp. Here is an example. Let's look at the 5-2 linear code C over the integers modulo 3. This code is defined by this 2x5 generator matrix over Z3. Note that the matrix has rank 2 because the last two columns of G are certainly linearly independent over Z3. Let's find a parity-check matrix for C. We'll first find a generator matrix for C in standard form, and this will be done by reducing G to reduced row echelon form. So we'll start with G and make this entry a 1 by multiplying the first row by 2. We get this matrix. Remember now that the calculations are being done modulo 3 because this is a matrix over Z3. Next, to make this entry a 0, I'll subtract row 1 from row 2, and I get this matrix. The matrix is now in standard form. So by considering this to be the matrix A, a parity-check matrix for C is given by minus A transpose and the identity matrix. So note that G is a 2x5 matrix, whereas H is a 3x5 matrix. We can write down the code C explicitly. It should have 3 squared or 9 code words. So here they are, and they were obtained by taking all the 9 linear combinations of the 2 rows of G over Z3. We can see that the code has distance 3 because the smallest weight of any non-zero code word is 3. The code has rate 2 over 5 because here k is 2 and n is 5. In the next video lecture, V3c, we'll see how a parity-check matrix of a linear code can be used to determine some information about the distance of the code. On this slide, I've summarized some of the properties of parity-check matrices. The most notable one is that the code C can be described as being the null space of a PCM for C. In other words, a vector x is a code word if and only if H times X transpose equals 0.
In the next video lecture, V3c, we'll see how the parity-check matrix of a linear code can be used to determine some information about the distance of the code itself. Take care and have a wonderful day.